Hi, today we're talking about refrigeration. In the last video, we discussed some concepts that matter when it comes to refrigeration. We spoke about heat, for example. We spoke about some thermodynamic aspects of how heat flows. And we also spoke about what it means for something to be cool or what it means for something to be refrigerated. So, this video is going to be all about how we accomplish that. And on my drawing board here, I drew a box once again. The smaller box, this represents the refrigerator, let's say, and this larger box represents the room. So, based on our discussions in the previous video, we know that this refrigerator, if the contents inside are cold, it means that there is less heat inside the refrigerator. But how did that happen and how we can accomplish that is what we will see in this video. So, we know that when this refrigerator is first put in this room, before it is even switched on, we know for sure that it is going to be the same temperature of the room. Or rather, in other words, it is going to have the same heat that the room has. It's going to be in thermodynamic equilibrium with the room. One of the ideas that we thought of in the last video for cooling down this refrigerator or this little box is to bring in something that is cold. So, to bring in ice cubes so that the ice cubes can absorb some of the heat, and that way you can make the refrigerator colder. But we also realized that that was kind of impossible because you couldn't infinitely continue to bring ice cubes into a refrigerator. If you wanted to cool something down and keep it cool for a long time, for days, you cannot keep bringing in ice cubes. So scientists, they decided to use some special kind of chemicals called refrigerants. Now these refrigerants, they can be gases at room temperature. Normally, they are gases, but they can condense or they can cool down and become liquids. And as liquids, these refrigerants can become very cold. So instead of carrying bulky ice cubes and putting them inside the refrigerator, scientists thought that we could just use refrigerants. We could use simple liquids. So the idea was that you would take a refrigerant that is really cool, cool enough that it is not in its gaseous form, it is in a liquid form. You take that refrigerant and send it inside your refrigerator. You send it inside the box that you want cooled down. So when you send the refrigerant inside and it is cool, it flows through the box and it absorbs heat as it flows. What happens when a liquid absorbs heat? When it absorbs enough heat, it changes from liquid to vapor state. So it takes up all the energy. So the liquid molecules, initially when it's cold, they're all tightly packed. But when you give some energy to it, when it collects all the heat that is inside this box, it gets a lot of energy and now it's free to move around. So it kind of spaces out, and what was liquid now becomes a gas. So by picking up the heat in this room, the refrigerant vaporizes, it evaporates. So it enters as liquid that is really cold. It takes up heat and it evaporates and leaves in vapor condition. So by sending this refrigerant in, we have actually accomplished what we wanted. We have taken away some of the heat that is inside this box, which means that we have made this box cooler. And we did that by evaporating a cold refrigerant. So this portion here is called an evaporator. The evaporator is what it's kind of at the heart of your refrigeration unit, and it is where the heat gets absorbed or the heat gets taken away. So mission accomplished, right? You introduce something cold, you picked up heat, and it's taken all of the heat out by vaporizing, and your box is now cooled. It now has less heat. But there is again a problem with this, which is similar to the ice cube problem that we had. Ice cubes were really bulky to handle, refrigerants are less so, but still, you cannot infinitely supply refrigerant. You cannot continue to feed your evaporator with refrigerant all the time, all day, or for years. You cannot do that. we have to discover a way to somehow reuse this same refrigerant. But the problem is that the refrigerant has now evaporated. We want liquid refrigerant. It is now in its vapor state. So, what we will do, or what is done in a refrigeration unit, is that all of this vapor is sent into. So, we need to do the opposite of what we did here. We evaporated the liquid here. We need to do the opposite before we send it back in. So, the opposite of evaporation is condensation. Turn the vapor back into liquid. So, that's what we will do in something outside the box called the condenser. The refrigerant flows through the condenser, and while doing so, it becomes liquid again. And it's just sent back in its liquid form. Sounds really simple, right? But this, again, is not going to be very effective. So this is the concept, but there's still a couple other things that we need to add here to make this a proper and effectively working refrigeration system. So let's see what is lacking in this drawing that we have first. So we said that we are sending cold refrigerant inside. So it is cold. It takes up heat and it evaporates. What I did not tell you here, which I'm not sure you realized or not, is that although it took up heat, it did not really increase in temperature. It can be a little difficult to understand at this point, but what is basically happening is all of the heat that goes in is being used to convert the liquid into gas. There is no heat that is being retained by the system, or there is no heat that is free to increase the temperature of the system. All of the heat is just enough to evaporate it. So even though it takes up a lot of heat here, even though it just vaporizes, it does not increase in temperature. So it's kind of at the same temperature when it comes out of the evaporator. It's still sort of cold. Sending a cold refrigerant into a condenser, we have a big problem. Because our idea here was to dump heat outside. And if you had looked at the last few videos, you would have understood that heat will only move from higher temperature to lower temperature. So, if the temperature in the condenser, if the temperature of the refrigerant in the condenser is not high enough, there will be no heat that goes out into the atmosphere. And therefore, there might not be any condensation at all, or there might not be enough condensation. Because heat is not going to go out. If this is not at a high temperature, heat is not going to go out. So, that whole temperature not being high enough thing makes this setup very ineffective. So, the way to fix that is somehow between the evaporator and the condenser, we have to somehow find a way to increase the temperature of the refrigerant before it reaches the condenser. To do that, we have something amazing called a compressor. What happens in a compressor is all of the gas molecules, the refrigerant gas molecules, are compressed. That's what happens because it's a compressor. They are compressed, which means they come closer together. And by bringing them closer together, you increase their energy so much that their temperature starts rising. So, when the refrigerant exits the compressor, it is still going to be vapor. You are compressing the vapor or the gas, but the difference is it is going to be much, much hotter. It is going to be highly compressed. For example, if the gas molecules were like this before the compressor, after being compressed, they become all clumped together at a very high temperature. So that's what happens. So this high temperature refrigerant is now sent into the condenser. Now it is at a high temperature or a higher temperature, and therefore it gives away heat. it dumps all the energy that it gathered here. It gained energy, here it's giving away all that energy, and by giving away energy, becomes liquid again. Hmm, do you see the problem there? There is one more thing that we need to add to this refrigeration system. So now that we heated up all of our gas at the compressor, just so we can condense it back to liquid, it did condense, but it did not really come down in temperature because just like with the evaporation, during condensation, the heat did go out. There was some energy that went out, but all of the energy that went out was only enough to change it from gas back to liquid. Additional energy did not go out. There was no energy beyond that that went out. There was no energy that went out that reduced the temperature. So even though it is liquid, it is still hot. And what is the point in sending a hot liquid back into the evaporator? It's not going to take any more heat. It's not going to absorb any energy. So why? We need to have something here, just like we did with the compressor, where we added energy to increase the temperature. We need to somehow reduce the temperature here before we send the liquid refrigerant back into the evaporator. And we have something amazing that goes in here. It's just a valve, but it's a very special kind of valve. It's called the Joule-Thomson valve, and it works on something called the Joule-Thomson effect. I'll tell you about what Joule-Thomson effect is first. So, Joule-Thomson effect says that when you have some molecules or any liquid or any fluid, if you expand that fluid, its temperature comes down. That's what Joule-Thomson effect is. Expand a fluid and its temperature will come down. A little bit of detail on how it works is, imagine that there's a liquid. Okay, let's just imagine here that there is liquid, and the liquid is kind of at high pressure because we compressed it here, and at this point it is still at a higher pressure. Across the Joule-Thomson valve, what happens is we reduce some of the pressure. So what we're basically doing is, by reducing the pressure, we are allowing the molecules of this liquid to expand. And by allowing it to expand, we are moving them farther away from each other. Remember that there is no phase transition here. It is still liquid on both sides, just that you are expanding it and the molecules are now farther apart from each other. Two molecules are actually attracted to one another, and when they are close together like this, there's a lot of attraction between them. And when you expand the molecules across the valve, they tend to move apart. But in order to move apart, they need energy because they need to break this force that exists between them. That energy they take from the fluid itself. And by taking in that excess energy, the temperature of the fluid comes down. The temperature of the liquid has come down now. So it is still liquid, but because of the Joule Thomson effect, the temperature of the liquid has come down. And now we are back to where we started. We have a cold refrigerant which is ready to go into the evaporator and pick up more heat. And that is how a refrigeration system works. And I think you'll agree with me now that this is very, very simple. So I'm just going to recap while labeling some of these elements here. This box is the evaporator. Cold refrigerant goes inside and evaporates. It picks up heat. Its temperature does not rise because it uses up all of the energy just to change from liquid to vapor phase. It does not increase the temperature. Now, this cold vapor now goes to a compressor because you want to increase its temperature before you can push the heat out. So, you compress it. You perform a lot of work here and you compress the gas into hot gas. The hot gas, which is now ready to dump all of the heat, comes into this, which is the condenser. And at the condenser, the refrigerant gas, which is now hot, gives out all of the heat energy. And this is why you'll notice that behind a refrigerator, if you kind of feel, not touch it, but just go feel the atmosphere there, it's kind of warmer. It's because the refrigerator is actually pulling in heat from inside and dumping it outside into your room. So your room actually becomes hotter at the cost of cooling down whatever you have inside. It only gives out enough heat for it to become liquid. It does not reduce in temperature. So it comes all the way to the Joule Thomson valve, where you expand it, you reduce its pressure and make it expand so that the molecules take up lots of energy from the fluid itself, from the liquid itself, to overcome the van der Waals forces and they become cooled. Now the cold refrigerant goes back in. Air conditioners work exactly the same way. The only difference is this right here would be your room, and the evaporator portion of the air conditioner would be inside your room. And the bigger box, you can imagine that's just the atmosphere. So, what the air conditioner would do is it would evaporate all of the refrigerant inside your room. So, it picks up heat from your room. And all of the other components are actually outside of your room. And it just dumps the heat outside into the surrounding. If you're interested to know a little more about different kinds of refrigerants or in more detail about the thermodynamics, then let me know in the comments. And if there is anything fundamentally that was not clear, then please let me know and I can make and explain a video for that as well. Thank you for watching.